Hi. Today we'll cover chapter 15 briefly, and it's about oscillatory motion. Chapter 15, oscillatory motion. Now, if you remember so far, we talked about object moving on a straight line, motion in one dimension, and then we moved on to object moving in 2 and 3 dimension space. Then we took an example of object going on circular motion, 2 dimensions. What is left, because these are motions we face in nature, you see them. We have what is called vibrational motion, oscillatory motion, something vibrating, like an atom or a molecule in chemistry, chemical engineering, oscillating, or a pendulum, a spring, when you pull it and start doing oscillatory motion. Okay? So we have to cover this motion as well, which means we have to know things about position, velocity, acceleration, time taking, all sorts of things which we talked about in chapter 2 and 4 and 5, yeah? Motion in general. So this is one of the motions which you have to know how to treat and calculate things related to. So we start with the first definition, periodic motion. What's a periodic motion? From the title, period, the word period, it means you have a period of time for something moving, yeah? So a periodic motion is a motion when you have an object start at a point and come back to there, and it repeats the motion all over. Okay, this could be like the earth goes around the sun. This is a periodic motion, yeah? It's repeating motion and back to the same point, and again, it's the same all over. That's one motion, yeah? Or a spring vibrating. So at any point, you see the spring goes and come back to the same point over a specific time, yes? Which we call it the period, time for one cycle. So that's general periodic motion, something repeating its motion on a time interval. Now, we have a special periodic motion. So we are still in periodic motion, but we call it simple harmonic motion. Simple harmonic motion. What's a simple harmonic motion? It's a periodic motion. But what's so special about it? This periodic motion, which we call it simple harmonic motion, simple harmonic motion, we call it SHM for short, simple harmonic motion. Simple harmonic motion. It's a periodic motion. It's an oscillatory motion. These are the words we use in this chapter. Oscillation, vibration, circulations, revolutions, all means the same thing, oscillatory, yes? But here, the best thing is to use oscillations. Something oscillates. So simple harmonic motion is an oscillatory motion, oscillations. But when do I have a simple harmonic motion? When I fulfill one condition, which is that the force responsible for the vibration follows Hooke's law. Hooke's law. And you all remember Hooke's law. It means the restoring force is minus kappa x. So what's the condition for a simple harmonic motion? You must have a restoring force similar to or fits Hooke's law, which means if the force responsible for the vibration does not fit Hooke's law, what we call it? Not a simple harmonic motion. Simple harmonic motion means the force is Hooke's law. As example, if you have a restoring force following this equation, do you call this periodic motion simple harmonic motion? No, because it's not Hooke's law. Hooke's law, linear with x. Okay. What about this one? Hooke's law? No. What is missing? Minus. And what does the minus mean? The x and fs are opposite. Here they are not. Okay? So you have to have Hooke's law as the governing force in the vibration. Now, if you look at it here, if you think of this as the equilibrium point of the vibration, you always find the Fs towards the equilibrium. Take it back to the starting point or the equilibrium point. So if this is the equilibrium, the force takes it to the equilibrium, right and left together. So this is a simple harmonic motion. Now let's take an example of a simple harmonic motion, which we all know. Hooke's law works for a spring or not? Okay, so if the spring vibrates, then its vibration is called simple harmonic. But what's the condition here? If you have a spring, you pull it and release it, will it continue oscillating or it stops? Why? Because there is friction. Okay? So the friction will make the spring stops, yeah? But when you talk about oscillatory motion, it means the system is conservative. No friction, no applied forces. If you want the object continue vibrating, oscillating, then you should avoid or applied forces on the system. So what we do here, we say we have a spring, but no applied forces, yeah? So if I have this spring, this is the equilibrium position. If you pull it to the side, anyone's got a ruler? Ruler? No? If you pull it to the side, of course here you are applying a force, yeah? Thank you. You're applying a force. But up to now, I'm not having a simple harmonic motion. No oscillation. When the oscillation starts, when I remove my hand, so there's no applied force, and there is no friction, then the spring will oscillate forever. Okay, how many forces do we have in the spring? We have Fg down, normal up. Those are balanced. And these two forces are not responsible for the vibration. But what are the forces on the x-axis? Only spring force, restoring force, yes? Fs. So Fs here is the force which gives you the oscillation. And Fs is Hooke's law, yeah? So what do I expect here? A simple harmonic motion for the spring. Which means now I can study this motion in details and see how can I get some equations which they talk about the position, velocity, acceleration. Now here, if I draw it here, if this is a spring here at equilibrium, x equals 0, it will vibrate between this point, x max, and back, and then to this side, we have another x max, but in the negative, yeah? Here positive, and this is the 0. So from here to there, we have the maximum extension, yeah? And this side, maximum extension. So when the spring vibrates between those 2 points, we have a simple harmonic motion. Now, what are the forces do we have here? Vertically, I have 2 forces. I have Fg and normal, and those are not responsible for the vibration. But horizontally, I have the force of the, as example here, the force of the spring this way, Fs. But here, so always towards the center. Huh? So on the x-axis, I have Fs equal minus kappa x. Hooke's law. Right. How many forces do we have on the x-axis? So how much is F net? What's the total force on x? Fs, same. So can I replace Fs by F net? Okay, so I say F net equal Fs equal minus kappa x. And what is F net? Ma minus kappa x. What is A equal to? Minus kappa over mx. All right? Let's put them here. Kappa is a spring constant. Mass, yeah? Both of them are constants. So what we'll do, we say those 2 constants, let's call them something else. What shall I call them? I'll call them omega square. Now, why square? Because it has a reason. You can call it omega. You can call it alpha, beta, but we decided to call it omega and square. It's a constant. It could be anything. So omega square is kappa over m. So what is omega then? Root of?
We take the minus.
No, the minus is outside. So now, what we have now? Equation, yeah? What's the equation now? Acceleration equal minus omega square x. Yes? This acceleration for the spring, yeah? Spring, acceleration. Now, what can you tell me about the acceleration here? Is it constant or variable? Depending on x. So when the acceleration is variable, can you use the equations of motion or you can't? You are not allowed. So in this chapter, you are not allowed to use v equal v naught plus 80. V square, v naught square plus 2a delta x. Delta x, v naught t plus half a t square. These equations for a equal. And in this chapter, or in oscillations in general, the acceleration is not. So it's not allowed to use these equations. And that's why we have to look for a new set of equations to solve the problem of the oscillations. So now our job is, what is the velocity function for something oscillating? What's the acceleration function? Of course, you know what's the acceleration function. What's the acceleration function? Minus omega square x. Yeah? This is for a spring oscillating. Okay? Now, whenever you see an oscillation following this equation, that acceleration is minus constant x position of the spring, we call the motion simple harmonic. So in simple harmonic motion, you have the acceleration and position opposite and directly proportional. Directly 1 to 1. Directly proportional. When x high, acceleration is high. When x is 0, it is 0. And opposite, negative. So when x is negative, what is the acceleration? What does it mean x negative? It means the position when you are on the left-hand side here, yeah? What is x here? This is 0. This is a plus. This is minus. So when x is a plus, this side, the acceleration is? And this side, the acceleration is negative, towards the left. Here, acceleration is negative, position is negative. So acceleration will point to the right, yeah? Based on that equation. Now, what do I want to do here? I mentioned this. Starting from this equation, a equal minus omega square x. Acceleration, we all know it's derivatives of velocity with time, yeah? Or acceleration is what? The second derivative of position with? Which one is useful here? First or second? Because I have x here, yeah? So if I remove a and I put second derivative, equal minus omega square x, yeah? Now, this is an equation, yes? A mathematical equation. It has a name. What's the name of this equation in math? General name. If we see an equation like that, what do you call it? What's the name of the equation? No, first, this is quadratic is wrong. This is not square. This is second derivative. It's not x square. Differential equation, well done. This is a differential equation because it has derivatives, yeah? So if you have a differential equation, what do? You have to solve it, yeah? Like you have a differentiation, yeah? This is rate of change, but the second rate of change. So you have to look for the function. If it's an easy one, of course, you just integrate techniques and you find the function. But if it's a second derivative this way, you have to learn the techniques of solving differential equation, which is beyond your course here. We don't, because some of you will do it, some of you will not. So there's a course in differential equation. Some of you do calculus 2 and 3 and learn it. But for the mass majority here, the solution for this equation is this. What is your function? X with t, yes? So you expect a solution, I write it here in the top. You expect a solution x as a function of time, yeah? Now, the solution of this equation, you find it's equal to a constant, a capital, cosine, omega t, this omega. Look, that's why we put it square. So because here it appears as power 1. If you put it as omega there, then you'll have a root of omega here. That was the reason we call this square. Because when you have the solution, you'll end up with omega, not omega square. Plus phi. Now, I'll tell you quickly why the solution of this one is this, using logic, no mathematics, just simple mathematics. What does this equation mean mathematically? X is your function, yes, which you are looking for, x. What happens to the function is being multiplied by a constant. So your function multiplied by constant. When your function multiplied by a constant is equal to what? Equal to the same function derived twice. It means there is a function x. When you derived it twice, it's equal to itself. You have a function, x. What did you do to the function? Derived it twice. When you derived it twice, it's equal to the same function or not? But multiplied by a constant. You can ignore this. This means the function equal to its second derivative. Which function in mathematics, when you derive it twice, is equal to itself? Which function? Cosine. If you have a function cosine, derive it once, becomes? Derive it again, back to itself or not? So that's what it means. Or maybe you say it's a sine. It's true. You can say it's a sine. Derive it, cosine. Derive it again, sine. Or it could be an exponential function, e to power x. If you derive it once or twice, it's the same, yes? But exponential function is not useful as a solution of oscillations. Why? Because the function is not repeating itself. It's not like sine and. So mathematically it's right, but physically it's not useful. Sine and cosine are useful. So now, you know now why the solution is cosine, yes? So the solution of this is a cosine function. Cosine function of time. So if you solve this one, it's just x t equal cosine t, yes? That's if you don't have omega. But because you have omega, the t will be multiplied by omega. Then if you say this is the solution, this is not quite true because you're saying that whenever this is 1, x is always equal to, which means your spring is always goes to 1 meter or 1 centimeter or 1 millimeter, which is not true. You don't have 2 centimeters, 3 centimeters, yeah? So what you need? A constant based on the vibration. What else? If you have a function like this, it means you always, your cosine starts from 0. And this is not true. You could have a cosine being shifted to the right or to the left. Remember in algebra? Horizontal shifting. So it means you need a shift. Did I do it without differential equation or not? Logic, yeah? The solution is a cosine. But the cosine is not quite with t because I have a constant. And then I need a constant here because I don't have always the value of the function is 1. So I need a constant. And then the function sometimes being shifted to the right or left. Horizontal shift, so I need a constant. I hope now you know the minimum here. But all what you need is that the solution is this. So I'll remove this one. That was big. Now, let's understand our equation. What is x? Is the position of the oscillator at any time, like here in the spring. If I ask you, after 1 second, where is the spring? Maybe it's here, or here, or here, -1, +1. Huh? The position. So this is x. Position of the oscillator at any. What is A? A is x. But which x? When all this is equal to cosine. What's the maximum cosine?
1.
When this is 1, what is x equal to?
A.
So A is the maximum x value. And A, which is maximum value, we call it amplitude. And it's equal to x max. Which means, in the oscillations, it means this. When the oscillator at the extreme point, this is A. And this side extreme as well. This is A but negative, but A always positive, it's a value. This side is negative, this side is positive. Omega, which I defined it before, what was the definition of omega?
Square root of k.
Kappa over m. And remember you have a spring here, yes? But generally speaking, omega, we call it angular frequency. Angular frequency. We'll come back to the definitions. Just remember, this is angular frequency. This is not work. This is not W, omega. Angular frequency. The last one is the phi. What shall I call the phi? We call it the phase constant. Phase constant. Phase. It's a constant. Remember, I call it, it's the shift in the function. Constant. It's an angle. Angle. Initial phase angle or initial phase constant. So now, do I have a function for x or not? So anything oscillate, I can tell after 2 seconds where it is. After 3 seconds. Or when I know the position is -2 centimeters, I can tell at what time. All right? So now we have an xt function. All right. If you have an xt function, can you find a velocity function?
Yes.
How? Derive it. So if I take this one and derive it, I'll do it there because I need the other side. So now the first function is xt equal a cosine omega t plus phi. Just remember, I chose cosine, yes, for x. You can find some authors of physics book, they start with sine. Okay. Yeah? But let's agree, in this course, we use cosine to start with, yes? But you can see a question, x is equal a sine. Possible. No difference. But stick to cosine here. And what is a? X max. Amplitude, yeah? Cosine omega t plus phi. Okay, I'll take this one. Now you see this one in your formula sheet for the final, this equation. Now, if I have xt function, how do we find the velocity function? Derive it, because v is dx over. Now let's derive this one. What's the derivations of cosine function? Minus sine. So the derivation would be minus sine omega t plus phi. And remember, you have already the amplitude, yeah? A. Now, when you derive a function, you have to derive the angle as well. What's the derivations of the angle? Omega. So you need an omega outside. So what is Vt function now for oscillations? Minus amplitude, angular frequency, sine, angular frequency t plus phi. Okay, listen everyone, carefully. What's the maximum value of sine? So when this is 1, what is V equal to? Minus A omega. So what shall I call A omega? It's a velocity, yes? But which velocity? Maximum, because this, the maximum value here when sine is. So now I can conclude that A omega is velocity max. So Vt minus V max sine omega t plus phi. Okay? Of course, what you have in the formula sheet, not this one, you'll have this one. But remember now, I learned two things. First, that amplitude A is x max, yeah? Maximum position. What else? I learned that V max is A omega. And we have A omega is V max. This is on the sheet as well. Now, the minus here, remember velocity is a vector, yes? When something vibrates, the options for the direction is either to the right or if it's a spring going up and down, up or? So the minus and plus means right, left, yeah? But V, when you take the magnitude, is speed. Same. Minus just gives you the direction. So yeah, I'm talking about the magnitude of the V. You can put minus, but doesn't mean anything, yeah? Now, if you have velocity time function, what can you do with it? Derive it again? Acceleration. So if I derive this one, I say acceleration is dv dt. What's the derivation of this? Start here with A omega. Of course, you can start here, but I want to keep the A and omega. So we have minus A omega cosine, 1 by 1. Derivation of the angle, another omega, this becomes square. So now, what is the acceleration as a function of time? Minus A omega square cosine omega t plus phi. Now again, maximum cosine is 1. So what does A omega square represent? Maximum acceleration. So can I write this one again? I say A as a function of time is minus acceleration max cosine omega t plus phi. Again, this is what is given on the sheet. Now, here, what's the conclusion? A max, omega, don't say W, because if you say W, it means work. Omega, this is angular frequency. Now, what do you see now? 3 equations of motion. One is xt, one is vt, one is at. That's it. We found the equations of motion for something oscillating, vibrating. Yeah? So all what you do now, you have to know how to find the A, omega, and phi. Okay? What is A? Amplitude. And what is amplitude? Maximum x of vibration. Omega, we call it angular frequency. I'll show you in a minute how to calculate it. And phi is the phase constant. It's an angle. Good. Let's go back to the PowerPoint here. It's handwritten. Okay. Now, let's define the 3 things which we need in oscillation. 3 things. First thing, which you already know. Period. Capital T. What is period? Time to complete before we call it 1 revolution in circular. Yes, here one oscillation. Time to complete one vibration. Okay? So this is the period. Now, in this chapter, I'll have two examples. One example is always the pendulum. Simple pendulum swinging. This is a simple harmonic motion, vibration, yeah? And another one, it will be a spring. You pull it and then release it, then start vibrating. So most of our questions are either a pendulum or a spring or general oscillator. You don't know what is it, but just something oscillating, regardless of it. So what's the period here when I have a pendulum? What does it mean, the period? It means the time to complete one. So if I start here, 0 time, yes? When it goes to there, how much is it? Half of the period. Period means the time to go and back. Complete. How much is the time from here to the lowest point? Quarter of the total, yeah? From here to there is half. Back, 1. Time to go and come back is 1 period. Now, the next thing, angular frequency, which is omega. Yeah? Now we come to the omega, which we needed, omega. What is omega? Angular. What does it mean, angular frequency? Angular means angle. Frequency, it means how frequent something changes the angle. How fast the angle is changing, yes? So if you want to define angular frequency, don't look at the definitions. I'll show it to you here. Think of this ball. Remember, we have a spring or a pendulum, yes? But circular motion is similar to vibrations as well. So you can always use the circular motion as an example of oscillation. And this is what you'll do in electrical engineering. Sometimes you use the circle to define oscillations of an electric circuit. So it's common because circular, similar to vibration. At the end, what does it do? Complete periodic motion. Back to the same point, yeah? Right. Now, if I have an object here now, at the moment, what's the angle of this object? On the x-axis, yes? What's the angle? 0. 0. 0. Now? 180, 270, 360, yes? Okay. Now, if this object rotates, similar to if this object vibrates. Now, let's say start here, up to here, let's say 30 degrees, yeah? 30 degrees? Yeah. Now, this 30 degrees is the angle. How long did it take to go from 0 to 30? It's a time. Now, if I have this object doing this, this is the 30 with a specific time, yeah? What if it does this? Look. It's the same 30, yes? But different? More time, yes? So to distinguish between those two, this is what we call angular frequency. The angle divided by the taking. Okay? So what is angular frequency? It's the angular displacement. How much is the angular displacement? How much did you displace it as an angle? Divided by the time. So omega is the rate of change of angle. Rate of change of the angle theta with time. Angular displacement. What's the unit? Unit of, okay, now, our equations are based on calculus, sine, cosine, tan, so it's not allowed to use degrees. It's radian, rad per second. Angular frequency. Now, look what I'll do, and you tell me what is omega now. What's the angle now? So if I start, go, and back to here, what's the angle? Don't use degrees. 2 pi, rad. Okay, 2 pi. That's the displacement, yeah? 2 pi. How long did it take? What is this time? One what? Time. I need time. What do you call this time? Period. So now, if I replace d theta by 2 pi, how much is the time for 2 pi? So what is omega equal to? Always 2 pi over period. 2 pi over period. And remember, the unit is rad per second. So this is one of the formulas for angular frequency. This omega for a spring, for a pendulum, or general? General. General. Okay. Now, if I have a spring, you remember when I used Hooke's law? What did I assume? What was omega s? We said it's root kappa over m. Okay. So now, can I combine those two? But when I combine them, they become not special, not general, special for a spring only. Because spring with general becomes for a spring. So combine them, you'll have root of kappa over m equal 2 pi over period of a spring. The time for a spring to complete one cycle. Now, rearrange in terms of Ts. What is Ts equal to? 2 pi. When you take this one down, then you can turn it upside down. So it becomes root of m over kappa. Again, this is the formula to find what? The time to complete one oscillation for a spring. Now, we finished now the angular frequency definitions. What is left? One more definition. Frequency, F. We talked about frequency before, but not in this term of oscillation, in circular motion. When you have an object rotating, circulating, it does revolutions, yeah? Let's say you have an object does 5 revolutions every 20 seconds. 5 revolutions every 20. So when you divide the 5 revolutions over 20 seconds, what does that mean? Frequency. Frequency. Revolutions over time, yes? But in this chapter, we don't use revolution. What do we use? Vibration, oscillations. So instead of saying revolution, what do you say? Number of oscillations per. So frequency is defined as number of oscillations per time. Frequency F, number of oscillations per time. Okay, let's do what we did with angular frequency again. Think of this ball now. Now this time don't talk in the language of angles. Talk in the language of oscillation. Starting from here, go and back. How many oscillations?
1.
So what shall I put here? Number of oscillation.
1.
Start and back. How much is the time?
Period.
Capital T. So what is the frequency equal to?
100.
That's the formula for frequency. 1 over. What's the unit of frequency? 1 over second, yes? And 1 over second, we call it hertz. Like with the radio frequency, yes? FMs, and hertz, megahertz, gigahertz. Number of oscillations of the signal per time. So now we've finished those 3. Now, remember these 3. Period, frequency, angular frequency. These 3. Whenever you know one of them, you know other 3. The other 2, sorry. Yes? They are linked. How they are linked? By this function. Let me put it here. Didn't we say omega is 2 pi over period? Yes. And here we say the frequency 1 over period. So what is angular frequency in terms of frequency? It's 2 pi frequency. Because this is 1 over T is F. Right? What I want to say that if you know period or frequency or angular frequency, you must be able to find the other 2. One of them is enough. Now, generally speaking, oscillation, which one is useful for you in calculation? Which one you need it? Look at the equations there. Omega. Because you needed the equations, yeah? Okay? So if it's in the equation, of course you know it. But if it's not there, unknown, use frequency or period to find the angular frequency. Good. So this is what we have. These are the three equations of motion. And this is the equation which I was talking about. Now, this part, how to find the phase constant, phi. Now, why I'm putting this title, remember how many things do I have in each equation? I have A, omega, and in all three. A, I know how to find it. What is A? Maximum X. Omega, how do I find it? From these equations. What is left? So now we have to know how to find phi. What is phi? Ignore this document here. It's not ignore it. You can look at it. But I have another way to find phi, which is much easier than this one, yeah? On the board. On the PowerPoint. So now, what's the title? How to find? The phase constant phi. Now, after all, what is phi? What's the definitions of phi? Phase. But what it really means, it means the angle. So if it's an angle, what's the unit for the angle? Radian, not degree. So phi measured in rad, always, no degrees. Okay. How to find phi? Easy. In any problem you have, when you read the problem, ask yourself this question. And once you find the answer, you are able to find phi. What's the question? The question is two parts. You say at time equals 0 second, which means at starting of the motion. At time 0, start motion. Ask yourself, what is the initial position, xi, of the oscillator? It's mentioned in the question. It says like, at time 0, the oscillator at x equal minus 3 centimeters, or plus 5 centimeters, or at 0. Are you with me? Yeah. That's just position. And position, remember, positive or? So this is the first question. Second question, same question. At t equals 0, what is the initial velocity? At time 0, at the starting time of the oscillation, what was the speed or velocity? Yes, velocity, of course, because this is v. So maybe you say we started with a velocity minus 3 meters per second, or plus 7 centimeters per second. Huh? So that's v initial. So now, once you find these two values, xi and vi, you are able to find phi. How? You go back to the equations of motion, which you have. You have xt function and vt function. So what do you say? You take the xt function, yes? You say x at 0. What is x at 0? xi, yes? What is mentioned in the question. But I'll use here symbols. xi equal amplitude, cosine. What is the time? 0. When the time is 0, so 0 plus. So now what is xi equal to? A cosine phi, equation number 1. Now the second condition. At time 0, what is the initial velocity? So where do you go? To the velocity function. So what do? You say v initial at 0. Remember, v initial is not 0. Maybe it's 0, but generally this is 0 for the time, not for the velocity. Equal minus a omega sine 0 plus phi. What is this equation? Equation number 2. Now, remember, when you have two equations, one with sine, one with cosine, how do you solve? Divide them. But divide them which way? So you have the sine in the top. So here you divide 2 over. So what we'll have? Vi as 0 divided by xi equal minus a omega sine phi over a. Okay, do I need the amplitude? Sine over cosine. So I'll have minus omega tan phi equal v initial over x initial. You are after phi. So what you say, tan phi. The minus, put it on the other side. Vi over omega xi. That's it. You don't need to do all this. What you have to do to find phi, what do you need? Initial velocity, initial position, and the omega. But put minus, don't forget. This is velocity, not speed. So sometimes the answer is positive, sometimes it depends on v. So if v is negative, negative, so the tan of positive. But if it's negative, it stays, yeah? So the angle based on that. I think this is easier. Yeah, this is easier than what we did.
The sign is not from the direction?
No, this is for the angle, tan. But the sign here is in the v and in the x. Because v and x, they have signs. Positive, negative. So put the values with the sign. I hope this is an easier way to find phi, yeah? So all what you have to do, find x initial, v initial, and omega, and this is your formula. But this formula is not given. This is a conclusion. Conclusion. Any formula which we conclude, you are responsible for. What is left now? Energy in simple harmonic motion. Energy. Now, it's the same pattern. What we did in the first chapters of this course, we were talking about equations of motion, then Newton's law. Then, when we reached chapter 7 and 8, we started talking about energy. And I told you that you are able now to solve the previous question by using the technique of energy, 7 and 8. Or you can use the old techniques. Same here in oscillations. We started with normal motion, yeah? Vt, xt, at. No energy concept. Now I move to solve the same questions of oscillation, but using the concept of energy. So that's why we call it energy in simple harmonic motion. So how do we use the energy concept in simple harmonic motion? First, simple harmonic motion, oscillatory motion, conservative or non-conservative? Conservative, which means potential plus kinetic at any point is equal to the potential and kinetic at some other point. And the total energy does not change. Initial total equal final equal total in between. E doesn't change, yes? So when you talk about energy, remember the equations you normally deal with. The first equation, E U plus. Now this equation is not for conservative, it's not for non-conservative, it's general. It tells you that when you add the kinetic to the potential, it gives you mechanical. In this chapter, sometimes we don't call it mechanical energy, we call it total. Same. So E is either total energy or mechanical total, doesn't matter. Yeah? So remember, this is total energy. Kinetic plus potential. Now, in oscillation, on top of that, we have Ui plus Ki must equal Uf plus, this is always true, conservative. Oscillation is conservative, unless you have an oscillation which dies out. We are not talking about this oscillation. We are talking about oscillation which continues without any change. All right. Now, this is true for conservative, which means for oscillations. And what do we have there? We have two examples, either spring or pendulum. So the U depends on the question. It's either mgh for pendulum or half kappa x squared if it's a spring. What else? Let's think of the pendulum. Take the example of, because we use it a lot. If you have a pendulum now swinging, what do we have? Oscillation. Of course, it dies out because there's air resistance, but we take the ideal case. It goes forever. You remember the lowest point? We take the reference here, yeah? At the lowest point, what type of energy do you have? Kinetic only, yes? Potential?
Zero.
Okay. Now, when it reaches the maximum, what happens? Stops, yeah? So what type of energy do you have here? Kinetic is 0. Potential is maximum. Here, potential is 0. Kinetic is here. Some kinetic. No, don't say half-half. In the middle, this is one of the common mistakes. The students think that, or general, that let's say this is 0, this is maximum 10, yes? They think at 5, you have half kinetic, half. This is wrong. In the middle, you don't have half kinetic, half. Why? Because your function is not linear. So it's not like 50-50, yes? Maybe it's 30-70. It depends on the location. So don't make this silly mistake. You'll find it in the review problems, some questions. It says at what point, at what x, you have 50-50. You'll find it's not in the middle. Anyway, so at this extreme, what's the energy? Only what? Only potential. Kinetic is 0. Here?
Only kinetic.
Now, this system is conservative or not? What's the total here? Kinetic. What's the total here? And those are equal or not? So what's the conclusion here? In a conservative system, E, mechanical energy, is equal to kinetic max. Because when you have kinetic max, U must be 0. So this is one of the formulas. When you calculate maximum kinetic energy, it's equal to total energy. What is the other one? E equal U max when kinetic is 0. But E is equal to U plus K general. Okay? Don't say E equal to K, wrong. It must be K. And when you say K max, it means half mv squared, which V? Maximum velocity. This is kinetic max. And when you say U max, half, if it's a spring as example, kappa what? X squared what? But X squared max. What is X max? A, amplitude. So what is U max? Half kappa A squared. U max equal to what? U max equal to what? So what is E equal to?
Half kappa
A squared, always. So total energy E is half kappa amplitude squared. Yes? This is always true. For a spring oscillating, the total energy of the spring is half kappa A squared. Of course, if you can say half M V max squared, if you have V max. Now, I'll prove that this is true now, based on what we're doing. Look here. E equal U plus K. Of course, what I'll do here is not like you have to learn it by heart. Just look at it, a bit of mathematics. We are just after the final equation. What is U equal to in a spring? Half kappa X squared, and kinetic half M V squared, general. X for something oscillating, constant or changing? Changes. What's the equation for it? A cosine omega t plus phi. Square the x. V, constant or changes? What's the equation for V for an oscillator? Minus omega A sine omega t plus phi. Square it. Now, open the squares, rearrange. Remember, omega squared is kappa over m. Put everything together. You will end up with this equation. E equal half kappa I squared. Which I already said it there, yeah? Without going through the math.
Doctor, this is only when the kinetic is 0.
No, but now E, regardless now, what is E equal to?
Half kappa A squared.
Sometime or always? Always. The total energy of a spring oscillating is always equal to half kappa amplitude square. Okay? That was the conclusions, but now I'm showing you that E is always half kappa A square. Okay? Now, go back now, take this E, put it back in the U plus K. Yeah. So what we are doing here? Replace E with half kappa A square. Replace the U with half kappa X square. Replace the K half M. What is common? Half, yes? Rearrange, put everything together, you end up with this equation. The final equation is interesting. Look at it. What does it say? This one. I want to summarize it here. When you talk about energy, remember these equations. Specifically, this one. This one, you don't need it because you know it anyway. This just tells you EI equal EF, yes? But you need this. E is always equal to maximum kinetic, or E is equal to? And this is the same as saying what? E equal half kappa A square. This is the central equation of energy. The rest are not there. Now, what is the final equation there? It says V equal plus minus omega root of amplitude square minus x square. Please pay attention to this equation. It's in your formula sheet as well. This equation has something which you don't have on the equations of motion, the three equations of motion of oscillations. This is velocity, yes? Okay. The equations of velocity which you have, what was it? What is V as a function of t for oscillation? Minus A omega sine. Okay, now I want you to compare this velocity with that velocity function and tell me the major difference.
No time and no phi.
No time. That equation, it gives you the velocity without knowing the time. But this velocity, you must know that? No, it's both of them specific. But that one doesn't need time. So if you don't know the time, can you find the velocity? Yes. By knowing what? Omega, which usually you know. Amplitude. But what else? So this is V as a function of X, position. If you know the position, you know the velocity. Without knowing the time. But if you know the time, you want the velocity, use that one. Okay? Now use this one on the other way around. It means I could have the velocity given, or the speed. What can I calculate? At what position the speed is 5 meters per second. Put 5, you find the position, but take the square of both sides, so I get rid of it. So think of this equation, you'll use it a lot, and useful. A question takes 1 minute using this one. Some of you will do it the other way around. How? You know X, yes? And instead of putting X here, A here, omega to find V, what you do? You know X, so what you do? You go to the equations of X. You have X, you go and find what? and you find t, you go and put t here to find. How much did you spend on this question?
Half an hour.
10 minutes, 15 minutes, yeah? And you got it wrong, definitely. And you say the time is not enough for the exam. Because you went in the wrong way and the hard way. This is the easy way.
But you will not bring an easy question. Only
Well, I mean, this is a formula. You have it. You think about how to use it, yes? So don't go the hard way. Go the easy way. You have x, you can find v without knowing the time. So this is the last equation of energy. These are the energy. Now, what is left now? I'll talk about the simple pendulum as an example. But quickly, I go through the pendulum because that was an example of the spring. Now, simple pendulum. Let me do it on the board. Where is the ruler? Simple pendulum. Simple pendulum, this is a simple pendulum. Do we have a periodic motion? Yes. No? But is this simple harmonic motion? I don't know. Why I don't know? Because simple harmonic motion needs Hooke's law. So if the force responsible for returning the ball to the center follows Hooke's law, then I say it's a simple harmonic. If it doesn't, it's not a simple. So let's see. If you have a pendulum like this one here, what are the forces in the pendulum? You have tension and gravity only, no air resistance, conservative. Now, tension is not responsible for the swinging because it's perpendicular. This is the radius, perpendicular on the arc or the tangent. So still we have what? Fg. But Fg in this position, not useful, yeah, mathematically. So if I say the tangent is the x-axis, where is the y-axis? Goes through the tension, yes? So now where is Fg now? Between x and y. If that angle is theta, this angle will be theta. So this will be Fg sine. This will be Fg cosine. Now Fg cosine will equal Ft. That's why the pendulum is not going up or it doesn't move like that, yes? But the pendulum moves on the arc. Which force on the arc? Fg? Any other force? So this is the force responsible for the swinging. Yeah? This is the restoring force. Now, if this is the restoring force, does it follow Hooke's law? No, this is not Hooke's law. This is F G sine theta. Hooke's law is minus kappa x. Of course, we have a minus here because the force here and the arc are opposite. We have a minus. So let's say this is Fs now. If you compare, they are not the same. I can think of the kappa as mg, yes? Constant, constant. But what's the difference? This is x, linear. This is sine theta, sine, non-linear. But if I make this one linear, then they match or not? Okay. In calculus, you learn something, which I remind you now. In calculus, sine theta is nearly equal to theta if what? The angle theta measured in radian, if theta in rad, what else? And if theta is small value. You can do this at home. Put your calculator on radian. Choose a small angle, theta, small. Small in rad, not small in degree. Of course, if you have degrees, like if you have 10 degrees, yes? How many rads is that? What's the conversions? Pi over 180, yes? So how many rads is that? This is 10. So pi over 18, exactly. How much is pi here? 314. 314 over 18. Quickly. 0.1 rad, yeah? Is this small or big? Small, okay, say small. So now, if you put your calculator on rad, take the sine of this, you'll find it's the same. What is sine of 0.17? 697. Sine theta equal? But what's the condition? radiant, and small. So now, if I choose the angle of the pendulum small, can I replace sine theta by theta? Allowed? Okay, so now I say this is Fs equal minus mg theta. But remember, theta here isn't rad. What else now? Theta in radian is defined this way. A radiant angle, theta rad, is defined as the length of the arc, S, divided by the radius. Theta rad is S over R. Now, where is the theta here? It's there, yes? What's the radius here? It's the length of the pendulum, not R, L. And the S is the arc. So I replace the R with L, yeah? Think of it the other way around. Yeah? Now, what can I write here? Minus mg, what? S over L, Fs. Let me remove this one now. You have this on the document there. I'm just showing you how to do it. Right, put the L down there. MGL S Fs. Now, look, compare Hooke's law with this one. Fs minus constant over constant. Similar to what is left? S. X is linear. S, arc. They are not quite the same, but here they are quite the same. Why? If you have an arc, small, then S and X are the same. I like the way you think on it. Look here. This is the pendulum in the middle, yes? Take a small angle, not big angle of swinging. Small angle is this. This is the arc, yeah? And this is the X. Is there a big difference between them? But if the arc is big, this is S, this is X, different. So can I think of S as X? Is this Hooke's law or not? But for a spring or for a pendulum? Now, in pendulum, I don't have kappa, but what do I have? Mg. So I can think of Mg over L. I call it kappa effective. It's not quite kappa effective. It's not a spring. If it's kappa effective, can I use the equation of spring now, which I know, but I use it for a pendulum? If you remember, we had Ts, period for a spring, 2 pi root mass over kappa, yeah? We had it in the beginning. Now, if I replace this kappa with kappa effective, so I can use T for pendulum, not for a spring. 2 pi root M, what is kappa effective? Mg over L. M with M. G over L, I can turn it upside down. So what's the period of a pendulum? 2 pi L over G. Did you remember? Yeah. This is the equation for a pendulum swinging, yes? When you are allowed to use this one?
Less than 10 degrees.
That's why in the lab told you, use 10 degrees or 5 degrees. Because this is valid for a small angle, not big angle. Okay? So this way I finished the theory. What I'll do, the example I gave you on the sheet, I'll go for the first example. Bear with me because you might find it. Now for the camera, just you can look at the first, just the example, just top. And I'll go through the day. And you can browse it through if you want. What I did here, I prepared 2 examples for you. Example 1, comprehensive, which means if you look at this example, do it yourself again. You don't need to do too much study of 15, because I took all the options. So when you do this, You are able to do the review. 90% of the questions are here in this document. But two examples. Example number 1 and example number 2. I'll cover example number 2 next time I see you. But I'll just go through example number 1, just samples. Example number 1, it's got part A, B, C, D, E, F, G, H, I, J, K. How many? So how many questions is that? More than 15 questions. I created 15 questions from one question. Okay, I will not go through all of them, you have them. But I'll give you a sample, yes? So I'll write what do we have here? I read the question just for the video. We have a block spring system oscillates with a simple harmonic motion according to the equation x equal 0.2, x equal 0.2, cosine 10t pi over 2, where x measured in meters and t in second. Now, the mass of the block which oscillates is 2 kilograms. So the mass is given as well. And we have here a spring oscillating. Okay? Now, this is the example given. What is the question? I can generate all these questions, yeah? So we don't, while I'm looking at this example, I generate the questions, yeah? So we don't need to look at the questions. What's the technique here when you have equation given for oscillations? The first thing you do, you compare it to the standard equation. Before you answer any question, compare it to the standard equation. This is xt function, yes? Compare it to the xt function. What is the xt function standard? A cosine omega t plus. Right, good. Now, once you do that, you already know three things. The amplitude, angular frequency, phase constant. How many questions are there? You answered 3 questions before anyone asks you a question. So now, what's the amplitude? Now, the unit depends on what x measured in. If it's centimeter, millimeter, because cosine has no unit. So the unit of x is the unit of the amplitude. Here it says meters, yeah? Omega, 10. 10 what? Rad. And phi? Pi over 2 what? Rad. The angles in rad. Yes? Right. Which one of these 3 is very important? Omega. Now you know omega, which means you are able to answer another 2 questions. Find what? Frequency and period. Omega is 2 pi over t. So what is t? 2 pi over? So we found t. Frequency? 1 over period, if you know the period. Or you say omega is 2 pi a frequency. Now, how many questions so far? 5, 6, 7, yeah? Right. Let's generate more questions. What is the maximum velocity of this oscillator? What do you need for maximum velocity? A and? Do you have them? Because V max is A, and you have both. What is the maximum acceleration? What is the total energy of this oscillator? What do you need for total energy? What's the formula for total energy? E half. Good. Listen here. This is something new. Look here. To find E, what do you need? A and? Good. Do you have A? Yes. What is left? This is a spring, yes? Yes. Where do you find kappa? In the omega of a spring. This is omega general here. What is omega of a spring? Kappa over m. Do you know the mass? Yes. 2. Kappa unknown. Omega is 10. You find? Square both sides. Put K here, you find? I want someone to tell me how to find E not using this one. I need another equation. What is E equal to? I said it a moment ago. U max is this. K max. E is? And how you find K max? What do you need? Half? Didn't you find V max? That's another way. All right? Now, what I'll do now, I'll choose a question which you need to evaluate. Because, remember one thing here. Whatever is inside the cosine and sine is in radiant, not in degree. But when you use your calculator on radiant or in degree? In degree. Then you have a problem, yes? So you have to switch it to? Don't switch it to radiant, sorry. Because you'll forget to switch it back when you do the other question. So I'll show you a technique now. You always use degrees, but it's in radiant. Remember, what you have inside the parenthesis is in radiant, not in degree. So let's take a question here. One of the questions, just give me more 5 minutes or 6. Yeah, before, I don't want to stop now because you'll lose. This is how to evaluate. H, part H. It says, at what time, no, sorry, not H, before H. F. What is the acceleration of the block at t equal 0.05 second? What is the acceleration of the block at t equal 0.05 second? I'll write it here. Find acceleration when t equal 0.05 second. Right? Let's see how we do this. Just think as if you didn't do anything here. The question, x is this, mass is 2 kilograms. What is the acceleration when this is the time? To find acceleration, what do you need? The equations of? So, what is the 80 here? This is xt or 80? How you find 80? Derive this one? Or write the standard A and substitute. I'll do it this way, because when you derive, maybe you forget something. What's the standard AT? Minus A omega sine omega t plus phi. Now, what is A here?
Omega squared cosine.
Thank you. Back to cosine. A omega cosine 10 t plus. So now do I have acceleration function or not? Now I have to evaluate this at what time? Okay, now before you do any evaluations, this is in rad or in degree? Always this one, put another bracket, say cosine, big bracket. You have the small one. Close it and multiply by 180 over pi and close the bracket. So now what do you have inside? Degree or rad? So are you allowed to use the calculator or not? Don't switch it to degree, to rad. Minus 0.2, 10, 80. Now let's evaluate. What is the time? So put 0 point there. I will not do it because you have the solutions. I just show you what to do. So this is minus 2. Cosine 10 by 0.05 plus pi over 2 multiplied by 180 over pi all square. Square, yes. Square. Thank you. So it's 20, yeah? Right. Now, what you do, number plus number, this is, remember, 314, not 180. This is 314 as well. What you'll have, one number, or what's this number? You'll have it in degree, yes? Then cosine this number, you have the answer. Is that okay? Before you do the cosine, before you take the cosine, before you use the cosine function, change all this to one number. And then cosine of this number. Don't switch the calculator to radian. Now, I'll do something opposite. The t is unknown. You want the x or the v, yes? Like h. H. H says, at what time the block at position 0.03? At what time? At what time x is 0.3 meters? Okay? Now, how do we find this one? What do you need? xt, vt, or at here? Because you have x. So xt, 0.2 cosine 10t plus what? Okay, we said this. I don't have to repeat. Before you do anything, you must multiply this one. Okay? Now this time, what do you want? The t is inside or outside? So what you have to do, because t is inside, you say all this, I call it z. Call it z. Yes? So what you have now? Cosine z 0.2 equal. What is x in this question? What is the next step? Cosine z is what? Over. And then what you say, z is the cosine inverse, yes? Once you do that, you have the value of z, yes? You go back, replace z with this bracket. So how much is z? Give me the z cosine inverse of that. It's still in degree, your calculator. I want to show you what to do. What's that? 1.42? Did you do cosine inverse or not? Don't look at the paper. Oh, you have the solution on the paper? No, don't depend on the paper. Maybe you're looking at step. 81.4. So it's 81.4 degrees. This is what? Z. But what is Z? Z, put it back. 10t plus pi over 2 multiplied by equal 81.4, yes? Don't open this bracket. It's ready. Take it to the other side. So 10t plus pi over 2 equal 81.4 multiplied by pi divided by? I shouldn't put multiply because it's my thing. Can you see now? This becomes radiant and this is radiant. Take the pi to this side, minus pi over 2, yeah? And then divide by? Okay, now you find that time, some time is negative. The answer time is negative, but time is always? What do you do in this case? Don't worry, put absolute value. Because in a sine wave or a cosine wave, you have time negative, time positive, but the same x. So it means just shift it by one cycle. You go to the other side. Leave it as it is, okay? Thank you.